Hello everyone, this is a video lecture for Linear Algebra Chapter 2. The goal here with these video recordings are going to be that we go through the whole chapter all at once. It's going to be kind of fast. I'm definitely not going to do every single problem, but I want to give you just a general overview of what each section has and maybe some key points to kind of look for as well. So let's start with 2.1, and they just title it matrices or matrix or something. So we've seen these. This is college algebra 1414, but it's been a long time. And so I'm just going to kind of update you and remind you about matrices here. So let me give you some examples. Let's say that I have matrix A is 1, 2, 3, 4, 5, 6. The size of this is a 3 by 2, 3 rows, 2 columns. I don't know, let's make up a B matrix. 0, 9, negative 7, 8, 3, negative 4. Cool. And this is also a 3 by 4. I'm sorry, a 3 by 2 as well. Try to put that a little bit better there. Okay. So some things. Let's just say that we're wanting to add some matrices together, adding A plus B. So this thing plus that thing. Will you, I guess you add common elements, like elements, so 1 plus 0 is a 1. 2 plus the 9 is 11. I'm trying to make that look like an 11 there. 3 plus negative 7 is a negative 4, and so on and so forth. This is a pretty easy thing to do here. You can also subtract them and all that kind of stuff. What about like 3a? So put a 3 in the front and then a. Well, 3 would distribute to each one of these. So 3, 6, 9, 12, 15, 18. That's pretty easy. Just distribute the 3 to every single number. What if I were to try to do a times b? Well, it won't work. I'm going to write here undefined because we have a 3 by 2 and a 3 by 2. The inside numbers are not the same. They're not the same. And therefore, you cannot multiply them together. Well, I'm just going to make up another matrix real quick. 0, 3, 6, 9. This is, again, a 2 by 2 now. And so what if I did A times C? Would that work? And yes, if that's a 3 by 2 and this is a 2 by 2. Notice that the inside numbers are the same. So that's good. That means like check mark. We can actually get an answer here. The result is going to come from the outside numbers. It's going to be a 3 by 2 result. So like whenever you start doing this, make sure that it's a 3 by 2 answer. Let's go ahead and do that. I want to just do this one with you. So 1, 2, 3, 4, 5, 6. And then I'm going to multiply it by the 0, 3, 6, 9. So this is my rows matrix, this is my columns matrix, and I know I'm going to get a 3 by 2 in the end. So 1 times 0 is going to be a 0 plus 2 times the 6. See how I'm going this way with it? So 1 times 0, 2 times 6 is going to be a 12. So like my ending number here will be a 12. If I do the first row, second column, I would have 1 times 3 is a 3. And then 2 times 9 is an 18. 3 plus 18 is a 21. Second row, first column. 3 times 0 is a 0. 4 times 6 is 24, so that'll be a 24. Second row, second column, 3 times 3 is a 9. And then 4 times the 9 is a 36. You add those guys together. I'm sorry, that's not a 36. Yeah. 3 times 3. And that, so I think I did it wrong on my paper. Anyways, 45. Yes, 45. Okay, moving on. Yeah, 4 times the 9 right there is a 36. I wrote a 27, so there you go. I mess up even on my papers. And so on and so forth. So let me just finish this one off here. This I hope I got 36 and a 69. I should probably check that. So 5 times 0 is 0, and then the 6 times 6 is 36. So yeah, we're good there. And then finally, 5 times the 3 is a 15, and then 6 times the 9 is a 54, and so that should make the 69. Yep, so that's good now. Okay, so even I make small mistakes. I'm not really concerned about small mistakes so much, because even I make them. What I'm looking for is that you have the concept down and you know what you're doing. So showing me that you can do this, obviously, one little number make a mistake, it's not going to be the end of the world. Okay. Some other things here in 2.1, they're saying that we can use this AX equals B format to solve for X and B and stuff like this. If you see this, what it really is an augmented matrix. And what we're going to do is RREF. Now, RREF basically is row reduced echelon form. For me, it stands for get the answer. And we did this a whole lot back in college algebra. I believe this is a -1 and a 2. And so these are going to be your answers. That's like x is equal to -1 and y is equal to 2, that kind of stuff. What we're doing here in linear algebra is that we're saying my answer is -1 and 2. Okay, basically they label this as like x1, x2, but really we used to just say x and y, but now they're just putting subscripts on them. So either way, same thing. How would I do this RREF stuff very quickly? I'm going to tell you, Desmos. So I go to desmos.com, Math Tools, Matrix Calculator, and you can easily do a new matrix. I'm going to add another column, 1, 2, 3, 4, 5, 6, and then I type RREF, open, A, close, and there's your answer right there. Super, super easy to do this sort of stuff. Okay, I recommend using Desmos along the way. So that was the overview for 2.1. What I want to do for each section is a problem from that homework, I guess you can say. Now, this is going to be somewhat close to what we're going to be doing on the quizzes. I tried to do a lot of proof questions, I guess you can say. And so this is actually a proof question. So here we go. Prove that if both products A, B, and B, A are defined, then AB and BA are square matrices. Now, this one's not on your quiz, but it's very similar. It's like 1 or 2 numbers off from it. So they're going to be different questions entirely, but it's similar in strength, I guess you can say, similar in complexity. So, and this one's actually going to be pretty easy here. So what are we going to do? And let's talk about proofs. I love talking about proofs here and how we're going to do them. I want to basically say that my A and B and A are both defined. They're not the same. They're both actual, answers. And so then they must also be squares. They should result in square matrices. Now, one thing to note, that A times B is not equal to B times A. Matrix multiplication is not commutative, non-commutative. So knowing this is one of those things I can't say they're the same thing. They might be, but not necessarily. So we have to watch out. Don't try to just do something silly like that, okay? So how do we get this started? Well, I'm going to assume that A is a matrix of size, I'm going to use C by D. I just want to use some letters, M, N, C, D, whatever you want to call them. And my matrix B is a matrix of size E by F. Again, I'm just making up these numbers. I guess you can even say C, D, E, F, elements of the integers that are positive. There you go. Whole numbers, essentially. So that's fine. I don't think you have to put that part, but I get the idea. They're sizes, C and D and E and F. I notice that I'm not using any numbers. I'm not just giving you an example. I actually am finding a proof general for anything here, okay? So I'm gonna show you on the side. Don't put this as your proof here, but let's just say 1, 2, 3, 4, 5, 6, something like that. So then we got a 2 by 3, and then again, I don't know. I'm just gonna make something up here that'll hopefully work here. 7, 8, 9, 10, 11, 12. A 2 by 3 and 3. Yeah, that might work. So this is not. You should not be doing anything like this on your proofs. Do not do this. This is just me just talking about it with you. I'm just trying to show you an example physically of what's going on. So I'm going to put like a little thing here just to delimit. This is not part of your proof. Don't write this as your answer. Don't even include it on your answers. This is, I mean, if you want to put it on the side just so that you're kind of talking to me about it, that's fine. But do not think any of this will give you credit. None of this gives you credit for a proof question, okay? And if you make it obvious that you're actually using this as your proof, then I would take off points. So please, on the side, say, not really part of what I'm doing, use a different color. I don't know. Just do not say that this is part of your proof. This is just you and me talking. So I got these two matrices, A and B, and I'm multiplying them, and I'm also like flipping them. So I got this guy over here and that one over there, and I'm still multiplying them and all that kind of stuff. What I want to do is say, okay, I got these numbers here, and yet I actually get an answer. Like, it's defined. It works in a way. And you can see right here, the reason why it works is because the inside numbers are the same. When I do this again down here, see how I flipped them, right? See how I flipped them? The inside numbers, again, are the same. So, you know, whatever I get out of that, it's going to work because the inside numbers are the same. That's the trick here. That's the key. Okay, so assume that I got these two matrices here. Again, hold on. I actually want to still write this. I got A, which is a C by D, and then I got a B. It's going to be multiplied. E by F. And this should result in my AB that will work. Notice that this here, if it works, these must be the same. Okay? So I'm saying that D equals E. Right here. Let's do the other way. Again, this is not your proof. If you do this, I mean, I get it. It's not proof, but at least you're kind of working through it. Okay, so here, again, I already know that I'm going to get an answer. I know that this works, this works, this works. So these guys must be the same. So I'm going to say F equals C for sure. These are going to be truths. These are statements that are true, and we're going to use them here in just a couple minutes, okay? My goal in the end is to say that if D equals E here, and this result here would be a C by F, right? And this result here is an E by D. Notice that if E and D are the same, and F and C are the same, then these are both square. Like, I just said that D equals E, so these guys are the same number. I don't know, 3 and 3, or 2 and 2, or whatever. Square. And here's F and C are the same numbers. C and F, square. So, I don't know, 2 by 2. It's a square. So that's the goal here. This is my goal. Let's kind of write it out now in proofy land, okay? So going back at the top, assume I got this guy and assume I got this guy, whatever sizes. Okay, cool. So how do I make this work in words, I guess you could say? AB is defined, thus my D equals E. Notice how quickly I state that. We just talked about it right here, right? And I just said, hey, look, there's my statement right there. And that's cool. Now, the point is that you don't have to give me a whole lot of work in order to do that. I understand what's going on. I got the answers to all these things. I did it myself, you know. So I just want to make sure you're going with the flow of it, okay? And then they make sense. You don't have to show me every single step. Don't make illogical jumps, but this is sufficient. This is fine. I mean, I'm understanding what you're doing here, okay? And so we got that. I also say, and my BA is defined, so thus my F is equal to C. Okay, cool. Keep going. The resulting matrix, my handwriting's terrible, sorry. Resulting matrix AB is size C by F. Okay, so I already know that. That's good enough. And because F equals C, AB is square. Okay, and then I would basically repeat myself. The resulting matrix BA is size, what did we say it was going to be? ED. And because we already said that D equals E, BA is square. Okay. So then I'm going to say now, therefore, we're done. So therefore, and you could even do it, I did this on my paper just because it was funny. Triple dot thing, therefore, A and B and A are square. And then you do a little box and call it a day. You're done. You could fill in the box if you feel like it. Some people do. Okay, that was the end of that proof. That was it. So, again, this is kind of more like, I would say, like a cartoon proof. Cartoon proof. It's more visual, you know, and this entirely defines what's going on here. This is not what I'm looking for. Don't do this. This is not good practice for this class. But this is what's going on. This is the physical, what's going on behind the scenes stuff, okay? So it's good to kind of draw stuff out for yourself. If you want to include something like that, that's fine. I don't count it. Again, this is your actual answer. This is what you need to do. So there we go. Okay, moving on. 2.2. We got properties of matrix operators or operations. Ops. Good enough. There's a whole ton of them in this section. I'm not going to do them all. A plus B equals B plus A. This is the commutative property under matrix addition. I don't want to write all that. C times A plus B is equal to CA plus CB. Again, distributive. So this is distributive property of scalars into matrices, blah, 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 blah. A plus the zero matrix is equal to A. So that's the additive identity. That's the additive identity. A plus negative A is equal to I. No, I'm sorry, 0. Sorry. We'll talk about I in a minute. Sorry. Equal to 0. That's the additive inverse. Additive inverse. And then we got CA equals 0 if C equals 0 or A equals 0. And so that's your zero matrix definition stuff there. Further on, we got A plus B multiplied with C is equal to AC plus BC. Now hold on a second. Hold on. This is an interesting little guy. This is distributive property from the right. Yeah? Which is actually a little different than distributive property from the left. I didn't write this on my paper, but I want to show you. What if I had a C on this side? Remember that AB does not equal BA. You distribute just like last time, right? So CA plus CB. What's going on is that it matters on what side you're multiplying on. Just keep that in mind again. AB does not equal BA always. Again, sometimes, but they are very rare instances. Okay, keep going. We got A transpose equals A. So transpose is basically just flipping it. If you had a matrix that was like a 1, 2, 3, if you transpose it, it's now going to be a 1, 2, 3 horizontal. So that's a transpose. So if you transpose, it's like you did it twice and you got back to the original. A plus B transpose is equal to A transpose plus B transpose. That's interesting. And then for the really cool one, AB transpose actually equals B transpose A transpose. See how they flipped? See how they flipped there? That's kind of interesting. They did not flip here, but they do flip there. Watch out for these kind of things. Again, I'm not listing all of the properties, just listing a couple. They like to talk a whole bunch about this stuff. That's nice. Moving on. So 2.2.62, another proof question. Prove the associative property of multiplication, and then they state it for you. CD times A is equal to C dA. Now, this is an interesting kind of question here. And I looked at this thing and I said, what? Of course it has to work, right? I mean, because a number times a number is another number and we're good to go. So how can I prove this thing? And that's fine to think like this, you know. There is a proof. We're going to do it. But I'm saying that there are some times where it's like, duh, you know, or wasn't that just given to me a second ago? Why do I have to now prove it? So we're doing it. We're going to do it here. It is kind of weird. I would recommend sometimes to go look on the internet. I know I talked about it in one of my announcements. I went and looked on the internet briefly. If you type this thing in to your search, it's just, there's a ton of things that come up, and it's not anything close to what you're looking for. But I was trying to look for an idea where to get started, right? So I didn't want the answer. I just say, like, how do I even get started on something like this? And I kind of had an idea when I started reading it, so I didn't not go far with that. I just said, oh, that's a good place to start. So here we go. I'm going to do mine. So assume my matrix A is size m by n, and then we also have C and D are elements of the reals. Basically, those are my scalars. Okay, so what I'm doing is I'm setting everything up. I got my C, I got my D, I got my A. Everything's good. Okay, so now I'm going to say assume B is equal to CD times A. So this is a new matrix. I'm basically just focusing on this side right there. And I want to say, okay, cool, we got my B is equal to this stuff. Well, now, I need to define what the individual elements are going to be. So I'm going to say such that my B subscript here, I, comma, J, I'm trying to put little dots here, subscript I, comma, J, equals that CD number, whatever that's going to be, times my A sub I, J sub I. I'm sorry, A sub ij. There we go. A sub ij. And this is where it gets kind of kooky, so I'm just going to put a comma here. Here we go. For all ij, so that's an upside down A, means for all. Okay, we're going to see other kind of weird numbers. I'm sorry, not numbers, symbols as we keep going. So for all ij, such that or when 1 is less than I is less than M, and that 1 is less than or equal to J is less than or equal to N. Okay, cool. Whew. What does all that mean? I'm basically saying for all elements. I'm saying for all of the separate elements in a matrix. You know, matrix has a whole ton of little numbers here, right? I'm saying, hey, for every single number in this matrix, this is what you're going to get is my result, okay? That's kind of what I'm trying to get at. But you have to make it look formal and pretty, and that's, well, proofs. So there you go. Okay. I might be going a long route when I go with this next one, but here we go. Matrix E is equal to dA, and I'm going to basically be repeating myself here. Dij, little dots. Give me some dots. Give me a dot. Okay. Is equal to D, and then Aij, and I'm going to shorten this a little bit by just saying for all ij. I'm not going to repeat myself every time. It's good enough. Okay. Assume then I'm going to do an F. Now is going to be a C times E. again, such that, lots of repeating myself, Eij is equal to C times E. No. Okay, hold on. I kind of messed up a little bit. Hold on. I'm getting there. And then see, I got a D right there, and this is a D. Hold on. Hold on. Well, you know, I can't be perfect on every recording, can I? So, well, now you know I even messed up. That's an E matrix. So this is an E right here. I don't know why I was doing a D. That made no sense. So that's a little E for this E right there. They're connected. And therefore, also, this will be now an F. Hope you're writing in pencil. And so then we got C times E again. See how it's A with little a, E with little e, Ij. Cool. But notice that this E here, we've already had it, is all this. So I could basically just substitute it in. That's what I'm going to do. So it's equal to C times D Aij. Okay. Again, for all Ij. I'm just shortcutting that one. I'm not actually giving you the dimensions every single time. So what I've got here is that I got this F matrix is equal to all this business here. And I got this B matrix is equal to all this business right here. Notice that these guys are the same, right? Those guys are the same. And technically, I think I didn't write this perfectly. I think I should probably do that. And now it's more proper. Let's do that. Let's just say this in particular. Now it's more proper. We're trying to prove this associative property stuff anyways. Because x, y, z is equal to x, y, z for all x, y, z elements of the reals. And so when I'm saying this here, I'm basically, and then I'm going to actually use parentheses here in my proof. I don't want quote marks. I'm going to actually say, I'll use quote marks. This is the associate. Whoa. Okay, hold on. Okay. Associative property for real numbers. Yeah. So, because, or according to the associative property of real numbers, my CDA sub ij equals CDAIJ. There's still subscripts, it just doesn't look very good, for all ij. Okay. Therefore, basically I'm saying they're the same. Those are the same, so we're good. Therefore, B equals F, just like I had said, that F and that B right there. Or CDA is equal to CDA. Now, let's just kind of zoom out for a second. We did it. We're done. I mean, for something that was pretty much a duh moment, look at all the stuff that we had to do. And I might have taken a long road here or there. Of course, there's a million ways to solve these things. But it's legit. That's what we're doing here. We got to make sure to cover every single portion. Notice that I am assuming the associative property of real numbers. That's pretty important. I'm not going to prove that here. Someone else gave that one to me. I'm just going to make sure that we can do it here with matrices. That's my point. We're building off other people's proofs too. Don't try to reinvent the entire mathematical system every time. 2.3. Inverse matrices. Inverse matrices. And so let me give you some, I guess, reminders about this stuff. A times B equals B times A is equal to I. If my I guess B is equal to A inverse. What's going on here is that This is kind of like, I guess, the definition of inverse matrices and stuff like that. Normally, AB does not equal BA, right? It's normally they don't really equal ever. But I'm saying that they will equal the same thing, I, which is my identity matrix, if they're inverses, okay? So some other ways to write this, which I find more intuitive than that. A times A inverse is I. A inverse times A is equal to I. All that kind of stuff. Notice that A inverse times A is different than A times A inverse, kinda. I'm not saying that they are different, because literally they're the same thing here. But it is important to distinguish multiplying on the left versus the right, and I will be using that here in just a couple minutes, okay? Let me give you a quick example of what I is actually equal to. So I is basically the 1, 0, 0, 1, 0 kind of stuff. That's your I matrix for a 3 by 3. Or for a 2 by 2, it looks like this guy. Or for a 1 by 1, it looks like that. Now notice the 1 by 1. This is actually important. I like to show this in class, is that we're just talking about the number 1. So like A times I is equal to A, because you're saying A times 1 is still equal to A. Yay! It doesn't change anything. That's the point. So we're kind of thinking that I kind of represents the number 1 in matrix land. That's how I see it, okay? Just depends on what kind of size you have. They often say IN just to kind of remind you, hey, it might have a size here. Let's do some other definitions here. That if my A inverse doesn't exist, then A, I'm going to put then, if then, A is non-invertible, or they'll use the word singular. Okay, so non-invertible or singular. Or the opposite would be invertible and non-singular. They are going to toss both of these words at you. There's not just one, oh, that one sounds better than the other one. No, they're just going to say invertible, non-invertible, singular, non-singular. They're going to use it all interchangeably as we keep going. So just watch out for that. They're the same thing. Non-invertible or singular. Same thing. Some properties that I've found were pretty helpful. We got A inverse is equal to A. So inverse of an inverse is that. My AB inverse is equal to B inverse A inverse. See how they flipped again? And then I've got AX equals B, which we had that, remember that R or EF row echelon stuff earlier. This has a solution of X equal to A inverse B. Now back in the day, we used to do this formula a lot more back in 1414. I think it still comes up a little bit, but it's not stressed nearly as much as what I remember. But here we go again. Again, you probably have forgotten all of that, and that is perfectly acceptable. We're not really assuming that you remember every single thing. Okay, so let's do a proof. 2,364. So prove that if A is an invertible matrix, there's an I in there somewhere, then A transpose inverse is equal to A inverse transpose. Huh? So this is an interesting little proof here. I actually started to do this whole huge thing, and I feel like I was messing up or maybe being too verbose. And so I went back and I just did something really basic. So I'm going to do something really basic with you, and it'll be fine. It's, I guess you could say, more mathy, which is good. So let's start it off. Assume that we have an A that is a square n by n invertible matrix. Now hold on Pause. We got to talk for just a second. They say that A is an invertible matrix. Cool. If you go through the chapter, the only invertible matrices you have are square ones. Only square matrices are invertible. So being invertible says that you're going to be working with a square, okay, a square matrix. So that's important. Go ahead and define that, make sure, you don't just say invertible and you keep moving, assuming something. I want to remind myself, because I didn't even remember. I was like, okay, wait. And so I went through, well, can I prove that it's a square number and all this stuff? That's not the point of this proof here. The point is, do this right here. So I'm assuming, because it's invertible, that it'll be square, okay? That's okay. That's a good thing. So I'm assuming right up ahead of time, here you go, assume, that we have a square one. Okay, but tell me when you're doing this kind of stuff. So because we have an invertible square matrix, all that kind of stuff, I'm just going to go into it. So what about this statement right here? Isn't that a true statement? True! It doesn't do anything. Just, yay, correct, yes. Well, that's a good place to get started, isn't it? If it's a true statement, we're good to go. And so let me start doing math with this. What I'm going to do, my next step here, I'm going to say A inverse transpose is equal to I transpose. Now, this is kind of interesting. You're transposing I. So, like, what is I again? And then you're going to transpose. You're going to flip it around. So this guy right here, you're going to convert this 2 by 2 to another 2 by 2. And it's going to look the same. So this guy here is actually an I. You don't have to prove this stuff. I know this. This is fine. This is good. I transpose equals I. Cool. Keep cruising. Well, what happens then is that if you remember those properties, I can toss this transpose in, but because they're multiplied, they flip. Like that. And then, of course, still equal to I. Cool. Okay. This is where it gets a little weird. I'm going to multiply both sides by the inverse of this thing. Okay, so like what I want to do here in the mini step. Here's a mini step. This is not a true step. It's just me kind of making it look pretty. Remove those parentheses here so you can make it look better. This dude right here, I'm going to invert him. I'm going to multiply by an inverse. And here we go. This is what it looks like. So I got my A transpose, and I got my A transpose inverse. Now notice I must multiply by the same thing on both sides. I must multiply by the same thing on both sides, and they need to be on the same side. That's a terrible English. Multiply by the same thing on both sides, put it on both the right sides or both the left sides. You can't just mix them. You can't say, oh, well, just put it in the front. No. It's got to be on this side. I know right now it's not important, but later on it will be. Okay. What happens is that this guy right here just actually cancels out. You could slash through it. I understand that. But essentially what's going on is this converts to an I. And then I say, okay, cool. Well, I times anything is just, it's like 1 times anything is itself. So I'm just going to remove the i's, if that's okay. There we go. Done. We just did it. Isn't that what they originally asked for? Right there. Cool, huh? See, and that was a lot more mathy. I mean, there are proofs that are mathy, and that's cool. It's fun. Yeah, you're seeing no numbers. I get that, but I'm saying, look, they're like steps. They're not just words all the time. That's pretty cool. Okay, keep moving. 2.4. Elementary matrices. So let me give you an example. What's going on? B is equal to, I don't know, E4, E3, E2, E1, and then A. These are elementary matrices. What they do is they represent a row operation. So each E sub I, that's a subscript. I know I'm not going to be doing this perfectly, but E sub I is a row operation. Now, we kind of skipped over row operations back, I think it might have been chapter 1. or maybe chapter 2.1, I can't remember. But like, this is not a big concern. When I say row operations, I mean RREF, okay? This is not something that was taught in College Algebra 1414 anymore, at least as far as I'm concerned. I certainly don't teach it anymore. And so this is something that will be new to you, but it's not hard, and we're going to get through it here together. So let me show you a little bit about what's going on. Let's just say, I'm going to make this example up if that's okay. Let's just say that I had my classic 1, 2, 3, 4, 5, 6 matrix. And remember that RREF, Desmos, will reduce this thing down to this guy, right? That's what my goal is. But I want to do this one by hand. Yep. So how do I go about doing this? So in a way, I'm going to ignore that I even did this here. This is all just an example. Let's say that I want to, let's say that I'm going to do -4 times the first row, add it to the second row. And often what happens in the book, many books, I'd say probably this book too, I can't remember, they just stop. They just say, there you go. And what they're trying to say is you multiply and then you add into row 2. But because I have this crazy thought of commutative addition rules and stuff, I like to add an equal sign to remind myself where this thing's going. So not required. The book will probably just do this, and just I want to add more for my own sanity. Okay. So why did I do this? What's going on? And blah, 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 blah. So -4, if I multiply this top row by -4 here, and then I'm going to add it into the bottom row, what I get is, well, first off, the top row doesn't change. That was a temporary number. Like, this is the only one that's changing. That's why I like to put an equal sign there. That's the only row that's changing. Don't multiply the top by -4 and leave it there. Gross. Just changing the bottom here. Well, then, -4 plus the 4 is a 0. I want a 0. See, look, aren't I getting that right there? That's the goal here. I got a -8. See how I'm distributing to everything? -8 plus the 5 would be a -3. And then I got a -12 plus the 6 is a -6. Okay, cool. Next step. What do I do? Well, I want to get this guy, so that was going to be a 0. I'm going to now get this guy into a 1. I'm going to multiply the bottom row, row 2, by -1/3. I'm basically doing the multiplicative inverse right here of this guy, multiplying it by the bottom. Again, I want to remind you that it's going to change only the top row. So 0 times anything is 0. That's supposed to be a 1. That was the goal. And then -1/3 times the 6 is going to be 2 negatives make a positive 2 out of that. Notice that we're already getting my numbers here, right? Look at that. My bottom row is complete. Keep cruising. I want a 0 here. We're very, very close. So how do I do it? -2 times the row 2 plus row 1. See how I'm saying the -2 is right here in the bottom? Multiply it and then add it into row 1. Only row 1 is changing. Here we go. So the bottom row stays the same. Go ahead and rewrite it. 0 times anything is 0 plus the 1 is 1. We should get that 0 there automatically. And then -2 times 2 is -4 plus the 3 is a -1. We're done. We did it. Okay, now what was the point of doing all this by hand? Elementary matrices. So we got to actually go back and write what my E matrix would be for each step. These guys here convert into a matrix. That's what they're saying. The statement, not this stuff, the statement, the row operation itself is a matrix. And so let me show you what this will be. This is E1, because it was my first one that I did. It's going to be a 1, -4, 0, 1. I'm multiplying it by row 1 and adding it into row 2. Multiplying it by row 1, adding it into row 2. Okay? E2, this is an actually pretty easy one. 1, 0, 0, -1/3. So I'm just simply multiplying by row 2. And then, I'm sorry, this is an E. E3, my last row operation. You probably guessed it goes right here. Okay. What I'm getting at is that if I did it in reverse operation, it's got to be in reverse. So this guy, E3 times my E2 times my E1 times my original matrix 1, 2, 3, 4, 5, 6 equals, guess what, 1, 0, 0, 1, and then over here a -1 and a 2. Don't put the augments here. It just doesn't make a lot of sense when you do this augmenty stuff in, say, a calculator. Of course, I use Desmos for this. I'm not going to show you how I did that because it would take forever. But basically, I got E3 times E2 times E1 times my A equals my B. So there you go. We just did that thing. Whew, that is one heck of a example. And off we go to a proof now. That has nothing to do with that. And that's fine. Of course, I need to show you that because this is on your quiz. This is on your homework stuff. So I'm glad we did it. So prove, this is my new thing, prove that if A is an n by n matrix, that is, and I'm going to try my best to say this, idempotent, and invertible, then A is equal to IN. Okay. What? Well, this thing, I went and looked, and I know it's on the quiz. You can basically just go look it up in the quiz. I went and looked through the whole entire section, didn't see that word. I went through the previous sections, didn't see that word. But I saw this all over the place in the homework, and the end of the section. Well, there's a separate little hint in the homework itself. Rarely does the book do this, but in the homework questions themselves, inside the homework questions, was this definition that you need to be able to answer the homeworks. Or the quizzes, at least, I guess. Isn't that weird? So that's weird. I know, we normally just look through the content of the chapter or the section. But here you have to read the actual math questions, and then they'll give you the hint finally. Very strange. A square, this is my hint, a square matrix is idempotent. I think that's how you say it. I don't know. When, let me try that over again. When A squared is equal to A. That's interesting, this square thing. I'm basically saying A times A is equal to A. Isn't that kind of weird? That's a weird thing to say. But we got this statement, okay? We got this statement. There's a hint on the side. And it's invertible. So I'm saying that this A inverse exists. I don't know what the heck it is, but it exists. Yay. Given these two things, prove that A is equal to I. Okay? So here we go. Here's the actual proof. Assume A is an n by n matrix that is idempotent and invertible. Now, just pause for a second here. Why am I just repeating what they already stated? Well, that's not a B, that's an is. Sorry. It just looked like a B for a while. Why am I just restating it here? Because that's what you do. So assume that we have what is called for. Thus, A times A inverse is equal to I. This is a known true statement because A inverse exists. So I got a true statement there. Cool, true. And so here's what's funny, though. I don't actually use this until later. We'll use this here in a minute, but yay, that's great. Moving on. A equals I. Now, just pause for a second. This is definitely a strange way of doing a proof here. But I believe it's still legit. I don't think everyone would make a big deal about it, but I'm going to go ahead and do it this way. I'm starting with a statement of, I don't really know if it works. See, I'm starting with the answer. I guess you could put an if in the front. So if, then, and then like you could do a whole ton of things with it if you want. I'm not gonna assume this. I guess in a way I kind of am. I'm assuming this, I guess, and we're gonna just work through it. Okay, that sounds kind of weird, I know. And if it sounds like I'm not very sure about it because it's weird. I'm starting with the answer, but let's just see if I can get something that's true out of this thing. Okay, so let's work with this and go from there. So if we got this, let me just kind of manipulate it a little bit. I'm gonna multiply. No. I'm gonna change my I to this A inverse thing. Right, my I changes to A inverse. Okay, so that's cool. That's cool. Okay, keep cruising. I'm gonna multiply by A on both sides. Ooh, you got to be careful. You got to multiply by A on both sides on the same handed side, the right hand side. You can't just put an A inverse or something weird. Got to put it on the same handed side, I guess you can say. Okay. What happens is that this right here is also an I. And so let me just go ahead and tell you that there. We got AA is equal to AI. And so then I got A squared, right? That's A squared is equal to A. And this was already assumed. This was assumed and blah, blah, blah. I don't have to state that. It's a true statement. So which is true. Therefore, A equals I. Put a box, call it a day. I think that's good enough. I like this. I consider this a good proof. If you wanted to be funny about it, couldn't you have gone in reverse? Couldn't you have started here and reverse step, all the way and got to this guy? Right? It's the same thing. So this still works as long as you get to the a true statement and an answer, I guess, in the way. 2.5. Markov chains. There's not a whole ton of stuff to talk about here. I'm just going to jump into an example here in just a second. But x sub n is equal to p to the n power x 0. What? P is stochastic? Stochastic? I can't pronounce this stuff. I just know it says this. What does that mean? Is that all the elements, numbers, I put numbers on my paper, all the elements in P are from 0 to 1. Okay, they're decimals, I guess you can kind of say. And each column adds to 1. Okay. So what is a Markov chain? Well, actually, let's just do a quick example of this P matrix. So I got the 0.8, 0.2. See how they add to 1. I'm just going to make something up. 0.4, 0.6. There you go. See, they add 1, and everything's a decimal. Okay, so what's the point of this Markov chain stuff? I would not be able to describe it well enough simply from this. I think the section in the book is pretty cool. It gives you like a lot more graphical representation. But essentially, you're looking for a steady state given a particular system of equations. Okay, a system. So eventually, it would run into a steady state of something or other. I'll show you what that means. Let's do an example. Okay, so this is not a proof question. This is just a numeric kind of question. And there's a lot more words than what I'm going to show you, but I'll do my best. 20% of people who purchase in this month will not purchase the next month. Okay? 30% of people, terrible handwriting, who did not purchase this month, they will purchase the next month. Okay. Whew. Whatever that means. There's 1,000 people total. and 100 purchased this first month. Go! Okay, well, hold on. So P is equal to, and what we're going to do here is say, aha, 20% have purchased, but they will not purchase the next time. So 20% is down here, thus 80% up there. On the flip side, for the people that don't purchase, I got a 0.3, because they will purchase next time. But the people who did not purchase and will continue to stay not purchasing will be the 0.7. Notice the way I had to design this. These are the ones that stay put. This is the purchase, this is the not purchase. Okay? So these guys are staying put. These are the ones that change. This guy's changing into a not purchase. This guy's changing into a purchase. Okay? So look out for that kind of stuff. All right, there's my P. My X not is going to be actually 100 that purchased and 900 that didn't. Because again, 100 purchased, 1,000 total. Awesome. The question here is actually asking for like px, p squared x, and all that kind of stuff. It's not too hard. You're just going to multiply these two in a matrix, Desmos kind of thing. I just use Desmos. It's very simple. In fact, let me just do this first one with you since I'm sitting here. So new matrix. I got a 0.2. No, I'm sorry. That's it. Whoa, let's start it over. 0.8, going across 0.3, 0.2, 0.7. And then I'm going to do a new matrix C. Remove one of the columns. There you go. And we got 100, 900. And so B times C. Boom. Done. That's my answer for the first one. 350, 650. Notice that I don't have to use P and X and Desmos. How do I get the square thing? I'm pretty sure you can just type the square, but here. So Shift 6 to pop it up into superscript. Put a 2 in there. Or you can just say, again, this could be B times C. Same thing, obviously. Not hard at all. So 475 and 525. Okay, awesome. What I'm wondering, not the 3rd, not the 10th. I want like the infinity. What's that going to be? Now this is bad notation. You're not really going to be doing that. What I'm looking for is the steady state. Now I can't remember if they actually ask for that here. Numerically, it's actually really simple if you're just wanting an answer. You can actually do a rough answer here. I'm going to say to the 10th power, let's say. And you can kind of see where my answer is going to start falling, right? Do you see my answer here is 600, 400, right? You can see it. It's pretty easy to see that. That's a rough way of doing it. 600 will purchase, 400 will not, kind of stuff. So there's my steady state. If they just ask for the numerics, you're basically done. That's not hard. What I want to show you, though, is how to actually prove it and do it correctly. So what we're going to have to do is px equals x and x1 plus x2 is equal to 1. Given that this, you're going to solve for x, which is going to be that steady state right there, basically. So how does this work out? It's kind of weird. I got my 0.8, 0.2, 0.3, 0.7 times x1, x2 equals x1, x2. So if I were to rewrite this thing out, multiplying this into here, you can see the 1 and the 2 equals the 1. And this is equal to the 2. And remember, also we have x1 plus x2 is equal to 1. So now I'm adding that in there. That's an additional little line. Super important for this problem. You can actually subtract this to the other side. There's a 1 right here, right? It's a 1. So I'm going to minus 1 onto the other side for both of these, making a negative 0.2, positive 0.3, 0. Then this will be a negative 0.3, 0. And then a 1x1, a 1x2 is equal to a 1. What you're really looking at here is a matrix. And what you would do is you're going to put this in to Desmos and RREF it. RREF. Now, I'm not going to do it just for speed's sake here. But what I got out of it was 1, 0, 0, 1, 0, 0, and a 0 down there. My numbers I got were 0.6 and 0.4. Now notice what's going to happen is I got the 1,000 times the 0.6 to get my 600. And the top 1,000 total times the 0.4 is equal to the 400 total. Awesome. That was it. We did it. So we got our steady state. Last section. We're almost there. 2.6 is actually going to go really fast. They just call this applications. And so one of the particular applications that is important to us, and that's going to be on your quiz, is the linear regression formula. Okay? So I'm going to do a mock version of kind of a basic one. They say that we got y equals x times a plus e, e being like an error of some kind. I think that it's a little weird. I don't really like this statement. I went and did the whole problem, and I thought it was kind of such that my a is equal to, and this is the real meat and taters, x transpose x inverse times x transpose y. That is your answer. And you're like, wait, what? And that's okay. You should be saying what. That's fine. So 2.6.29. Oh, what is linear regression? I'm assuming that you already know it. Maybe you do. Linear regression is basically we have some dots going out here, and we need to make a best fit line. There you go. That best fit line has an equation, y equals mx plus b kind of stuff. And that's what we're looking for. Okay, so given some amount of dots, find the y equals mx plus b for that. Now, could I just go do that Desmos or, GeoGebra or something else? Yes, of course. Could you use your calculator? Yes, of course. But how is that solving it? And I propose that some might be using this matrix method. Who knows? So here we go. I don't know what the problem was at all. I just took some numbers from it. I didn't even know what they asked for. I just decided to start doing this particular part here, okay? Just wanted the numbers. Okay, so I got my x's and y's. So to start solving, I want x transpose x is a component. Notice that we're going to be doing these components here. So the x is technically not just these numbers here. You're needing to do the coefficients, thus 1, 1, 1, 100, 120, 140. You're wondering why the 1's in the top. That's your constant term. Remember that this is mx plus b, right? Or rather, what they're going to be doing here in matrix land is b plus mx. The 1's, there's a 1b, and then this mx thing. So what I'm actually doing, the m is what I'm going to solve for, the x is what I can plug in. I guess so in a way I'm rewriting it like b times 1 plus m times x. And notice that I'm going to have the 1's and then the x's. Now this is the transpose. So upright, it should be 1, 1, 1, 100, 120, 140. And I'm going to multiply those, and I got 3, 369, 369, and then 46601. Okay. So now x transpose y, what would that look like? 111, 100, 120, 140, and I'm going to multiply it by just the y values here now. Very simple. 75, 68, 55. And my answer here was a 198, and then a 238. 8 right there. Let me try to make that not so messed up. 8. Okay, hold on. This one looks kind of messed up too. 198, 238, 55. Okay, Whew, you do not have to do all these steps here on the quiz. I think it even says that. Don't do all of the steps, just set it up. Something like that. I can't remember, but these are going to be my components, and so I want to do my inverse of the first one here. Like, in a way, I'm kind of doing too much. That's what I'm kind of getting at. This is 198. And then I got the 23855. Multiplying those, again, Desmos, whatever. I actually got decimals. I left it as decimals. A lot of times you can just get fractions and stuff, and that's fine. I'm feeling decimals today. Negative 0.41104. Notice that we got my B and my M, because again they wrote it in B plus MX format, and that's what we're going to be writing here. So this is my answer: 116.558 minus 0.41104x. There's your equation. We just did it. And I'm done. That's all of chapter 2. Whew, that was a lot. So I hope this has been helpful to you. It's been helpful for me, of course. If you have any questions at all, let me know. And know that I'm not perfect. I'm sure you're not perfect. Nobody's perfect. So, little mess ups, mistakes, you can talk to me about them. I want to help you out. I would even suggest you to send your rough drafts of your proofs to me. So, like, if you're kind of like, well, I don't know if I'm doing it right, send it to me before the due date. That way I could take a look at it, and I could say, oh, well, just, change this step here, or I see where you're going, but maybe change it this way or that way. I don't want you to just be blind to see if, like, you're not going to get it right or not. Who knows? I want to work with you. So please work with me. I'll work with you on all this stuff. Have a great day. Thank you very much for watching the recording.